Hello, we want to now look at an example of Newton's second law applied to rotation. So if you remember, for rigid bodies, fixed axis, rotation, we have a law which is torque is equals to I times alpha. So that's we want to apply that. So and this is torque. Each force will apply torque and cause alpha. But then if you're looking at net alpha, then you get a net torque. Net alpha is also simply we write alpha. So that's the law, and we want to see how that applies to a situation like this. What is the situation is we have a wheel. So this is the wheel, this part, and it's got a little axle here and supported, and you can rotate the wheel, and we'll assume that you can rotate the wheel without any friction. So you can just assume that is over here is no torque, no opposition. So we will assume so-called frictionless bearings or something like that. Mechanism down here. All right. There is a tape that's wound on the wheel, and some of the tape is coming out, and I pull on it with some force F, and this thing start to rotate. If you I'm going to work out non-numerically first, but later on we will say if this thing is 20 kilogram, radius is half a meter, and to pull steadily, so this is steady force. So that means constant. I'm going to apply 5 Newton, 5 Newton as I pull, same amount of force, and horizontally. So that's what this is constant means. So these are numerical values I'm going to apply later. But the questions I want to answer here is, what's the angular acceleration of the wheel? What's the angular acceleration of the wheels? As I pull, the wheel will rotate. But I'm not interested in just rotation speed. I want to know what's the acceleration, how fast. Initially, omega equal to 0 at t equal to 0. So initially it's not rotating. I start to pull at a constant force. It's going to start to rotate, right? It's going to start to rotate, and I want to know how quickly it's going to pick up the speed. Not the speed itself, but how quickly the speed picks up. And that's the acceleration. I can use the acceleration to answer questions like how many turns in the first 1 second. How many times is going to rotate in the first 1 second? I can also answer a question, how many turns is going to rotate in the second 1 second. I can also answer questions like how fast is rotating after it has unwound 2 full turns. So some of these questions I will be able to actually do all of it here, but some I'll just give you the answer for this numerical value so you can practice. All right. So let me. We already the law, and this applies to a system. So our system is the wheel. So system is the wheel, not the tape. That's the system. And I want to figure out the net torque. That means I need to figure out all the forces in the wheel that will cause torque. So first need to list them or kind of work through it. Forces. So we need forces on the wheel that will have non-zero torque about the axis of rotation. About this axis. So because I want to answer this question, that means I really need to know what is the axis of rotation for this problem, right? So what do you think is the axis of rotation of this problem? Is it like that? Is it like that? Is the axis that way? No. Axis is actually going through right at the center, and axis is coming like this way or going in. Either way, but axis is the line that goes through the center perpendicular to the drawing. Okay, so that's the axis. We notice that. So any force that's parallel to this axis gonna have zero non-torque. Any force that goes through that point will have zero lever arm, giving you zero net torque. Right? It's gonna give you zero net torque. So I'll just need to first list the forces so I'm clear about which ones are there. So here is the axis. This is this force F. That's the one. Then there are other forces which, using the symmetry of this of the wheel, we'll say the weight acts right at the center of gravity, which is the weight, which right through the axis. So we know torque of weight is zero. Then there are, if these are only two forces, the whole thing will accelerate in that direction, right? So there is some force at the axle that's balancing that. So there are these hidden forces inside there, not so hidden, we don't need them for the torque. We can call this F1 and F2, which we are not interested in this problem. We may be interested in some other problem, but here we're not. So, but I want to list them down, so I know I've considered them. So, and this is my axis coming out of here. So the only one that's going to have is this. This is the only one that has a torque non-zero, and I need to figure out the torque of F. Well, how do you figure out torque of a force? Do you remember how you do that? Think about it, and maybe you can work that out. Pause the video and work that out. And here is, for those of you who still are not clear about that, is there is step one. So step one is a line of force. Line is step two is draw from this axis point to here 90 degrees line to line of force at 90 degrees. Then that is the lever arm for F. That's the lever arm for F. And in the diagram, that's the radius. So from here, I get line of force of lever arm for force. F is the radius of the wheel. That's what I got. This is equal to the radius of the wheel. So now we have this. So I can write down confidently torque of F is this number times that number. So R times F. And I need to say it's a clockwise or counterclockwise because that's right, that's direction. And so for that, the decision is if the axis is this way and I'm looking down at the axis, then it's clockwise. So all of these are zero. When I add them, that's zero. So this is the net force. This is tau net also. So when I look at that, I got this guy done. And so if I know this, I can just divide by that to get alpha. All right. So I need more space. I'm going to erase here, and I want to make sure that you really understand what's going on here in terms of very detail. So we found that tau net equals R times F, and this is clockwise. Now I want to know what I is. Well, the system is the wheel, right? System is wheel, and the axis, to find I need to go back to drawing. Here is system. This is the thing that's going to rotate, and here is the axis. And axis is perpendicular to that. For this situation, the moment of inertia is half times m r squared. So the disk formula. So I got tau, I got I. So now I use this to get alpha. Therefore, alpha is equal to, I'm not going to write alpha net, I'm just going to write alpha. Is tau net over I. I is a positive number, so it doesn't change the orientation or direction. And so I'll get I just take this and divide the magnitude with that. So I have RF over half mr squared, and the direction will be clockwise. I can simplify, so 2 goes over there. One of the m's got cancelled out. So this is F 2F over m r clockwise. Okay, so we can do numerical values now. We can do numerical values to get the rest of this stuff. So numerical values will be alpha. So the alpha magnitude 2f 2 times 5 Newton, and you have a mass is 20 kilograms, 0.5 meters. So everything is in regular units, so I don't need to do a conversion. C for clockwise. So this one just becomes 10 kilogram meter, and they're all going to cancel out, and there's going to be 1.0 radian per second square, and this is going to be clockwise. Okay, so I got the one done, so this is done, and that's the answer for one, numerical answer. So alpha equals to that. How many turns in first 1 second? So this is numerical value, so we just use this to work now. I'm going to erase all of this. So for the second one, we are going to use this steady. F is steady, alpha is constant. That means can use constant alpha equations. And what are those? To get how many turns in 1 second. So I don't need to know what the final speed is. So omega at 0 is 0, and so if I use delta theta equals omega 0 t plus half alpha t squared, I would be okay. So if this is clockwise and this is 0, if this is 0 plus half alpha is clockwise, we can just say clockwise is a plus. Okay, so I don't need to worry about it. Or clockwise, we can say clockwise is minus and counterclockwise is plus. So the alpha clockwise, I put a -1 radian per second square, and then I have a 1 second duration square, and then I get a minus half radians, because minus is a clockwise, so it's changed clockwise. And the question is how many turns. I have an answer in radians. So delta theta turns is the positive value. This is not asking me, clockwise or counterclockwise. So you have a half radian, and I need to convert radian to turns. In one turn you have 2 pi radian. One turn, 2 pi radian, and there's 1 over 4 pi turns. So that's the answer for 2. How about how many turns in second 1 second? Think about what I would need. So if t goes this way, I have a 0 here, 1 second here, 2 second here. So I need, this was 0, omega was 0. So if I need to know omega over here, to already know alpha there, alpha is minus 1 radian per second square. So if I can figure out this guy out, I can use the same formula to get that. So how do I get omega at 1 second mark? Well, we just get this guy. So from here, omega at 1 second mark is omega at 0 second mark plus alpha t. And so alpha is 1. So 1 times 1 is this minus 1 actually, minus 1 radian per second. So you can use this in this this time frame to get 3. So let's see, I'm going to write this out. In here will be omega delta theta. In here will be minus 1 times 1 seconds, so this many radians, plus half times minus 1 for alpha, and 1 second square. And so this will give me minus 1, and this will give me minus half. So this is minus 3/2 radians. How many turns is that? Well, that means 3 over 4 pi turns for this guy. How fast is it rotating after 2 turns? I'm going to just give you the answer. You can try to find out. So here we are looking at delta theta is given to you. Omega 0 is 0 at the beginning. So how fast is rotating? It's 0 time here and 2 second mark here. So delta theta is 2 turns, is 2 times 2 pi radian, and alpha is given as minus 1. Delta theta will be minus, and this will be minus 1 radian per second square. So using this, you can find out its t is not known. Okay, it says 2 turns here. Means delta theta will be, and it's unwinding in a clockwise, so 2 times 2 pi, but I put a minus sign there, radian. So these are known, and what's the omega f? So that's what you have to solve. Okay, I'm going to stop the video here and post it. See you next time.